Welcome to a brand new deep dive from NEXGROW. This one's tailored specifically for mining engineering researchers and professionals like you. Today, we're going to be taking a close look at artificial neural networks and how they're being used in mining operations.
It's really fascinating to see how ANNs have kind of gone from like a niche research area to being like an essential tool for mining engineers.
Yeah, exactly. We're going to be exploring 3 research papers that span from 2008 to 2023.
So we get a really cool perspective on how the field has evolved.
Yeah, exactly. And we'll be starting with Bayesian Model Selection for Artificial Neural Networks by Kingston et al. That was from 2008. Then we'll move on to Protocol for Developing ANN Models by Wu et al.
Coalition 2014.
Yep. And finally, we'll be delving into Exploding the Myths of Artificial Neural Networks for Environmental Modeling.
That's a fresh perspective from 2023 by Mayer et al.
Yeah, in this range of research, it really lets us see how the thought and methodology of ANN development has changed over time.
It does, yeah. We can compare and contrast the different approaches and identify those key takeaways that are going to be relevant for today's mining professionals.
Right. And I'm sure a question on many of your minds is, how can we be sure these ANN models are reliable?
Yeah.
That they're accurate, especially in mining environments, which are complex and unpredictable.
Right.
So let's dive in and find out.
Okay, sounds good. So the first paper by Kingston et al., it tackles this really fundamental challenge in ANN development. It's about selecting that optimal structure for your model, and more specifically, determining the right number of hidden nodes.
Oh, yeah. I've always found those hidden nodes to be a bit mysterious. It seems like finding the right number just involves a lot of trial and error, which can be, super time-consuming.
Right.
And it doesn't always guarantee the best result.
Yeah, and that's exactly the issue Kingston et al. Address.
Okay.
They propose using this more systematic approach that they call Bayesian Model Selection, or BMS for short. And this method basically helps us to choose the best model from a set of candidates by considering both how well the model fits the data, but also how complex the model is.
So instead of just kind of throwing different structures at the wall and seeing what sticks, we have a more statistically sound way to make those decisions.
Exactly. That's a good way to put it.
Yeah.
And a key aspect of BMS is this concept of model evidence, which basically tells us how well a particular model explains the observed data. So the higher the evidence, the more likely that model is actually a good representation of the real underlying process.
So it's not just about fitting the data perfectly. It's about finding that balance between accuracy and simplicity.
Exactly. In BMS, it actually automatically favors those simpler models, which is, in line with Occam's razor.
Right. The simplest explanation.
The simplest explanation is usually the best.
Yeah.
And this preference for simplicity, it's really important in mining because we need those models that are interpretable and easy to explain.
Right. We don't want a black box that no one understands.
Right.
So how did Kingston et al., how did they actually put this BMS approach into practice for ANNs?
So they developed this framework that combines something called Markov Chain Monte Carlo Simulation, or MCMC, with methods for estimating that model evidence. So MCMC is a really powerful technique that allows us to sample from these really complex probability distributions, which is essential when we're dealing with the uncertainties that are inherently there with ANNs.
Okay, I'll admit MCMC sounds a little bit complicated. Can you give us a simpler way to think about what it does?
Yeah, so think of it as a way to explore a vast landscape of all the possible models. Right, so MCMC lets us take these random walks through that landscape, visiting different models, and then we evaluate their evidence. And by doing this over and over again, we can actually start to identify the areas of that landscape where the best models are hanging out, where the highest evidence is concentrated.
So we're letting the algorithm explore all the possibilities and kind of guide us to the most promising ones.
Yeah, exactly. And to make it even more concrete, Kingston et al., they suggest a really clever way to check the results by looking at the distribution of the weights that are assigned to the connections between all those nodes.
Right, those weights
in the network.
They always feel like the key to understanding what's actually going on inside.
Exactly, they are, yeah. So if the distribution of a particular weight includes 0, it actually suggests that the corresponding node might not even be necessary. It's almost like the network is self-pruning to get rid of complexity that it doesn't need.
So by analyzing those weight distributions, we can potentially simplify the model without sacrificing accuracy.
Exactly.
Okay, very cool. So this paper basically gave us a new powerful tool to select the right ANN structure.
It does.
But building a reliable ANN model involves a lot more than just picking the right number of hidden nodes, right?
This does, yeah.
Yeah.
Which brings us to the next paper by Wu, Dandy, and Mayer.
Okay.
This was published in 2014. The paper is titled Protocol for Developing ANN Models, and it shifts that focus from structure selection to a more holistic view of model development.
A protocol. Sounds like a recipe for success.
In a way, it is. They basically lay out a step-by-step protocol for building these robust and reproducible ANN models.
Okay.
And this is especially important, in mining engineering because the consequences of those inaccurate predictions can be really significant.
Right. We need to be able to trust these models to make important decisions, so having a clear and transparent process is essential.
Exactly.
Right.
And a really key point that Wu et al. Emphasize is the importance of documentation.
Okay.
So by carefully documenting every single step, from preparing that data to validating the model, we ensure that the whole process is transparent and reproducible.
Documentation might not be the most exciting part of, ANN development, but it's definitely crucial to building trust and ensuring that others can understand and replicate the work that we're doing.
Exactly. And their protocol is particularly relevant to mining engineering because it really highlights the importance of domain knowledge.
Right. It's not just about blindly applying an algorithm. We have to use our understanding of the mining processes to inform the development of those models.
Absolutely.
Okay, cool.
Yeah.
So, for instance, when it comes to choosing our inputs, they emphasize picking inputs based on both their significance and their independence.
They do, yeah.
So it's not just about throwing every possible variable into the model. We need to be a bit more selective with the inputs that are truly relevant and provide unique information.
Exactly.
And we need to make sure that we're not using inputs that are too correlated, because this can lead to overfitting.
Overfitting.
Where the model is basically memorizing the training data instead of actually learning those underlying patterns.
Oh, yeah. Overfitting. That's a trap I've definitely fallen into before.
Yeah. It can make your model look amazing during training, but then it fails completely when you apply it to new data.
Exactly. And Wu et al., they suggest a bunch of different techniques for handling this, including something called rotation of input vectors, which can be really effective at dealing with those correlated inputs.
That sounds interesting. So we've carefully selected our inputs. What's the next step in this protocol?
So data splitting is next. And they emphasize that it's not as simple as randomly dividing your data to training, validation, and testing sets.
I'm starting to see a pattern here. It seems like every step of ANN development needs a more nuanced approach than I initially thought.
It does, yeah. It's more than just throwing data at an algorithm. So with this data splitting, Wu et al. Really highlight the importance of creating subsets that are actually representative of the entire data set. Right. So this helps to prevent bias and make sure that the model can generalize to new data, which is super crucial for those real-world applications in mining.
Right. So we need to make sure that each subset has the full range of variability and patterns that are in the data. This sounds pretty challenging in mining because we often deal with data that's highly skewed or that has extreme outliers.
It is, yeah. And those outliers can be a real pain.
They can, yes.
But Wu et al., they give us a solution for this. They recommend techniques like DUP-LEX, which is based on Euclidean distances, to create these more balanced and representative subsets.
DUP-LEX. Okay, so instead of just randomly assigning data points, we're strategically selecting them based on how far apart they are.
Exactly.
From each other.
Yeah.
Okay, that makes a lot of sense. DUP-LEX. I'm going to have to look into that. And speaking of looking into things, Wu et al., they also go into the world of different ANN architectures.
Yeah, so they talk about different architectures, things like multi-layer perceptrons, MLPs, recurrent neural networks, RNNs, and generalized regression neural networks, GRNNs.
Wow, so many different types of ANNs.
There are, yeah, and each one has its strengths and its weaknesses. And choosing the right ANN, well, it really depends on the specific problem that you're trying to solve and the type of data that you have.
Right. No one-size-fits-all solution.
Exactly.
Got it.
Then Wu et al., they take us through model calibration, which is where we train that model to learn those relationships between the inputs and outputs. And they talk about the very widely used backpropagation algorithm, highlighting both deterministic and stochastic approaches.
Right. Backpropagation, that's where the magic happens.
Yeah.
That's where the model actually starts learning from the data.
It is, yeah.
Making predictions.
Exactly.
Okay.
And then once that model is trained, we move on to the super crucial step of model validation.
Okay.
Which is all about making sure that the model actually makes sense in the real world.
Right. We want to make sure that it can accurately predict outcomes in real-life situations it hasn't seen before, not just on the data it was trained on.
Exactly. So for this, Wu et al., they emphasize going beyond just looking at the predictive accuracy. They recommend using techniques like sensitivity analysis, which can help us understand how changes in the inputs affect the model output.
So we can kind of see how the model reacts to different situations.
Exactly.
And make sure it's behaving in a way that aligns with how we understand those mining processes.
Yeah, it's like you're having a conversation with the model, asking it, hey, why did you make that prediction?
I like that. So Wu et al. End their paper with a really strong message.
They do.
They're basically urging us to really scrutinize our model development process. This protocol they've laid out is like a checklist.
It is.
To make sure that the ANNs we're building are as trustworthy and as robust as possible.
Absolutely.
This protocol feels like an essential guide for anyone working with ANNs in mining.
Yep.
It's full of practical advice and reminds us that building a model you can rely on, it takes planning, attention to detail, and a healthy dose of skepticism.
I agree. Now, to round out our deep dive, let's fast forward to 2023 and look at the work by Mayer et al. In their paper, Exploding the Myths of Artificial Neural Networks for Environmental Modeling.
Myths. I'm intrigued. Tell me more.
Well, there are a lot of misconceptions surrounding ANNs, and Mayer et al. Directly address these myths and give some really valuable insights that are very relevant for mining engineers.
Okay, let's hear it. What are some of the myths that we need to bust?
So one of the most common myths is that ANNs always need these massive amounts of data to be effective.
Right. That's what I always hear. You need mountains of data to train these models.
Yeah. But Mayer et al., they challenge this notion. They argue that the quality of the data is often more important than the quantity. They emphasize careful selection of the inputs, thinking carefully about your data pre-processing, and really incorporating that domain knowledge can make even smaller data sets work really well.
That's good news for us mining engineers, because getting those large, high-quality data sets can be a real struggle.
It can, yeah. It's not about drowning in data. It's about using what you have smartly. Right. And another myth they tackle is this perception of ANNs as black boxes.
Okay.
You know, with no interpretability.
Yeah, that one always makes me a bit nervous. It's hard to trust a model if you have no idea how it's actually making its decisions.
Yeah, and I get that. But Mayer et al., they argue that while the internal workings can be really complex, there are techniques like sensitivity analysis and weight inspection that can help shed some light on how those decisions are being made.
Okay, so it's not a totally hopeless situation. There are tools to help us understand what's going on inside.
Exactly.
Okay, good.
And then finally, they talk about this myth that more complex ANNs are always better.
Right, more is always better. That's what we're told.
Yeah, well, not necessarily Mayer et al. Highlight that really complex models can overfit the data, and then they fail to generalize to new data. So it's about finding that sweet spot between complexity and performance, much like what Kingston et al. Were talking about earlier, with finding that optimal structure.
It's really interesting how these papers from different years are kind of all pointing to the same underlying principles.
They are.
Which is thoughtful model development, understanding the limitations of the data and the models themselves.
Absolutely. And that's the value of looking at research from different perspectives and over time, right? Seeing how the field has evolved and identifying those core principles that are still super relevant even as new techniques come out.
It's been a really insightful discussion so far.
Yeah.
We've explored different methods for selecting the right ANN structure.
Yeah.
We've looked at a protocol for building those reliable models.
Yeah.
And even busted some common myths along the way. I feel like we've got a good foundation now for understanding the key considerations for ANN development in mining.
I think so too. But we're not done yet. In the next part of this deep dive, we're going to get more into the practical aspects of actually building and refining these models. We'll look at things like input selection and data splitting in more detail.
Awesome. Stay tuned, because we're going to get even more hands-on with these ANNs.
Welcome back to our deep dive into the world of artificial neural networks for mining engineers. In part one, we kind of explored the evolution of ANN model development, focusing on selecting that right structure, those robust protocols, and debunking some of those common myths. Now, let's shift gears a little bit and dig into a challenge that often pops up when we're building these ANN models, and that's picking the right inputs.
Right, input selection is super important. I remember Wu, Dandy, and Meyer, they really stressed picking inputs based on both significance AD independence, but how do we actually figure those factors out in practice?
That's where it gets really interesting. Wu et al., they actually review a bunch of techniques for assessing how significant the relationship is between those potential inputs and the output we want. And they group these techniques into two categories, model-free and model-based.
Model-free versus model-based. So is that all about whether we need to build a preliminary model to evaluate the input?
Exactly. Model-free techniques, well, they don't need a separate model. They rely on analyzing the data itself to find those relationships. One common example is correlation analysis.
Oh yeah, correlation. We use that all the time in mining to understand how variables relate to each other.
Yeah.
Basically, are two things moving together or in opposite directions? But what about more complex relationships? Can those model-free techniques handle that?
They can. That's where techniques like mutual information come in. It's a more general way to measure association, capturing both those linear and nonlinear relationships. And this is really helpful when we're dealing with those complex mining processes where those simple correlations might not be enough.
So if I think my inputs have a more complicated relationship with the output, I should maybe use mutual information instead of just correlation.
Exactly.
Okay, that makes sense. So what about those model-based techniques? What's the advantage there?
Model-based techniques, they involve building a simple model first, like stepwise regression, just to get an idea of how important the different inputs are.
Right, stepwise regression, I've heard of that. You add or remove inputs one by one and see how it affects the model, right? Kind of like dipping your toes in the water.
Yeah, that's a good way to think about it. It helps you pinpoint which inputs have the biggest impact on the output. And there are a couple of different versions, like forward selection and backward elimination, each with its own way of adding or removing those inputs.
So it sounds like we've got some good tools for figuring out input significance. But what about independence? How do we make sure our inputs are giving us new information and not just repeating each other?
Right, and that's where techniques like principal component analysis, PCA, come in, and that rotation of input vectors we talked about earlier. These methods transform the original inputs into a new set of variables that aren't correlated. These are called principal components.
So we're basically creating a new set of inputs that are independent, getting rid of any redundancy. It's like we're cleaning up the signal before feeding it to the ANN.
Exactly. And by using these principal components as inputs to the ANN, we can reduce the risk of overfitting and maybe even improve the performance.
That's clever. We're making the inputs more ANN friendly. Now, Wu et al. Also talked about clustering. How can clustering help with choosing inputs?
Clustering algorithms, they group data points that are similar together based on their features. And we can use this on those potential input variables to find groups of inputs that are very correlated.
Okay.
Then, instead of using a bunch of correlated inputs, we just pick one representative from each cluster.
So pick a champion from each group to keep things simple. I like it. But with all these techniques, it can feel overwhelming. Any advice on how to choose?
You're right. There's no magic solution. The best choice really depends on the mining problem you're tackling, what your data looks like, and what resources you have. And sometimes combining a few different techniques can give you a better overall picture of those inputs.
So use our engineering judgment and knowledge about the mining process to make those choices. And I remember Wu et al. Said to document all of this, right?
Absolutely. That documentation is super important, especially in mining, where the decisions we make have big consequences. If we can't explain why we chose some inputs and not others, it's harder to trust the model's predictions.
Right. Documentation might not be glamorous, but it's really important for accountability and trust in the model. Okay, so we've covered input selection, a super important step for building reliable ANN models. What other challenges do we need to watch out for in this world of ANN development?
Data splitting is another one that often catches people out. Remember, we have to divide the data we have into those different sets: training, testing, and validation.
Yeah.
But doing this right is trickier than it might seem at first.
Not at all. Mentioned that just using random splits can be a problem, right? We said we need to make sure those subsets are statistically similar. Why is that so important?
We want to make sure each subset represents the whole data set, that it captures all the variability and those patterns in the data. And this is especially important in mining, where we often have data that's skewed or has those outliers we talked about.
Right, those pesky outliers can really mess things up if we don't handle them properly. How do we mitigate that?
That DUPLX technique we mentioned earlier can be really helpful here.
Okay.
DUPLEX creates balanced subsets by picking data points based on how far apart they are in that input-output space.
So instead of randomly assigning data, we're being strategic about choosing points to make sure each subset covers a wider range of those data characteristics.
Exactly. It's a more deliberate way to split the data, reducing the risk of bias and helping the model generalize better to new data.
I'm seeing a theme here. Whether it's selecting inputs, splitting the data, or picking the right ANN structure, it's all about being thoughtful and understanding the nuances of the data we're working with.
You got it. ANNs are powerful, but they're not magic. We need to handle them carefully and really understand the problem we're trying to solve.
So we've split our data, making sure each piece is representative. What's next in our ANN adventure?
Now we get to the heart of the matter, training that network to learn from the data.
Training. This is where the model starts understanding how those inputs connect to the outputs. What's the key here?
The most common algorithm for training ANNs is called backpropagation.
Okay.
It's a process where the model adjusts its internal settings, things like weights and biases, to reduce the error between its predictions and the actual values in that training data.
Weights and biases, those are the things that control how the ANN makes its predictions. I've always wondered what they really represent and how the model knows how to change them.
You can think of weights as the strength of the connection between those neurons in the network.
Okay.
And biases, they act like thresholds, deciding how easily a neuron will fire. During training, backpropagation uses a technique called gradient descent to find the best values for these weights and biases.
Gradient descent sounds like we're going downhill, hopefully towards a solution.
Great analogy. Imagine a mountain range where the height at each point represents the model's error. Gradient descent starts somewhere random and gradually moves down the slopes, changing those weights and biases until it reaches the lowest point, where the error is the smallest.
So we're guiding the model down that error mountain, adjusting its settings until it finds the best solution. I like that.
Yeah.
But what controls how fast it moves and in what direction?
That's where the learning rate comes in. It's a parameter that controls how big of a step the model takes during gradient descent. Choosing the right learning rate is important to make sure the model finds a good solution without overshooting the target.
Careful decision-making again. It seems like building a good ANN is all about making informed choices at every stage.
Absolutely. It's not about randomly tweaking things. It's about understanding your data and your model.
Speaking of understanding, validation is the next step, right? How do we make sure the model is actually good and can be trusted?
Validation tells us whether we can trust the model to make good predictions in the real world. And to do this, we need to do more than just see how well it does on the training data.
Right, I've fallen into that trap before. A model can do great on the training data, but then fail completely with new data.
Exactly, that's overfitting. And to avoid it, we need to test the model on a separate data set that it hasn't seen before. The validation set.
Okay, so we have the training set for teaching the model and the validation set to check its understanding. What about that testing set I keep hearing about? Where does that fit in?
The testing set, that's the final exam for our model. It's a completely separate data set that we use for the final evaluation. We don't touch it until the very end, after we've fine-tuned the model with the training and validation sets.
So it's like a simulation of a real-world scenario where the model has to deal with completely new data.
Exactly. The testing set gives us an unbiased assessment of how well the model will generalize to new situations.
It seems like we need to be really careful about how we use our data throughout this whole process.
We do.
From selecting inputs and splitting the data to training and validation, it's about avoiding bias and making sure the model can handle new information.
You're right. It brings us to another important point about validation. We need to look beyond just accuracy.
Wait, there's more to validation than just seeing how many predictions the model gets right. I thought that was the main thing.
Accuracy is important, but it doesn't tell us everything.
Okay.
We also need to look at things like precision, recall, and the F1 score.
Okay.
These metrics give us a more complete picture of the model's performance, especially when we have imbalanced data sets, which is common in mining.
Imbalanced data sets. Remind me what those are.
An imbalanced data set is one where the different categories we're trying to predict are not represented equally.
Well,
for example, in mining, we might have a data set where most of the data represents safe conditions and only a small amount represents hazardous conditions. Oh, right. I see the problem. If the model just tries to get the most predictions right overall, it might just learn to always predict the most common category and ignore the less common one. That wouldn't be good for safety predictions.
Exactly. That's where precision and recall come in. Precision tells us how many of the positive predictions made by the model were actually correct. Recall tells us how many of the actual positive cases the model was able to catch.
So we're not just looking at overall accuracy, but how well the model does on each specific category we're trying to predict.
Right.
But how do we combine those two things into one metric?
The F1 score does that. It's a way of combining precision and recall into a single number that balances both considerations. And it's particularly useful for those imbalanced data sets we often see in mining.
Okay, so we've got accuracy, precision, recall, and the F1 score. It sounds like we've got a whole toolkit of metrics to evaluate our ANN model. Is that everything?
Not quite. We also have techniques like sensitivity analysis, which we talked about before, and residual analysis.
Sensitivity analysis helps us see how changes in the inputs affect the model's output. It tells us which inputs are the most important.
Okay.
Residual analysis looks at the patterns in the model's errors, which can show us potential biases or places where the model needs to be improved.
Wow, this validation process is really in-depth. It shows that building a trustworthy ANN model is an ongoing process, not just a one-time thing.
Exactly. And speaking of ongoing, we often need to go back and refine our model based on what we learned during validation. We might need to adjust the model structure, change those training parameters, or even revisit how we selected those inputs.
This is a cycle of continuous improvement.
Precisely, and that's what makes it so interesting. By embracing this iterative approach, we can make our ANN models more accurate, more reliable, and more trustworthy for making those critical decisions in mining.
This has been such an eye-opening deep dive. I'm feeling a lot more confident about understanding ANN model development. But I know we're not done yet. What else is coming up in the last part of this deep dive?
We've laid the groundwork, but there's still one key aspect of ANN model development that we haven't tackled yet. Interpreting the results. How do we get meaningful insights from these complex neural networks? That's where we'll pick up in part 3.
I can't wait to open that black box and see what's inside. Stay tuned for the grand finale of our ANN deep dive.
Welcome back to the final part of our deep dive into artificial neural networks for mining engineers. We've covered a lot of ground already, haven't we?
We have, yeah.
From choosing that ANN structure, understanding those robust protocols, and data splitting and validation.
Yeah.
Now, we're going to talk about what I think is probably the most mysterious part.
It can be, yeah.
And that's interpreting these ANN models and figuring out how to get some useful insights from them.
Right, yeah. Interpretation, it's often seen as the final frontier in developing these ANNs.
Right.
Is where we're trying to connect those powerful algorithms to human understanding and trust.
Right.
Which is so important in mining, where the model's predictions lead to real-world actions and decisions. Exactly. We've talked about how ANNs can sometimes feel like black boxes.
Right.
It's tough to really grasp how they're making their predictions. So how do we shed some light on what's happening inside?
Well, there are several techniques that we can use to peek inside those black boxes.
Okay.
One that's used a lot is sensitivity analysis.
Oh, yeah, sensitivity analysis. I remember we talked about that a bit when we were discussing validation.
Yeah.
But how does it help us specifically with interpretation?
So think of it as a way to probe the model and see how it behaves.
Okay.
We basically change the input variables one at a time,
Okay.
keep everything else the same,
Right.
and then we watch how the model's predictions change in response. This can pinpoint which inputs have the biggest impact on the output, giving us insight into what's driving the model's decisions.
So it's like we're doing a controlled experiment, sort of poking the model to see what makes it tick?
Exactly. And by actually quantifying how sensitive the output is to each input, we can learn a lot about the inner workings of the model and any potential biases that might be there.
That makes a lot of sense. So for example, let's say we find the model is super sensitive to an input that's really hard to measure accurately in real life.
Yeah.
That would be a red flag, wouldn't it?
It would. It suggests the model might be relying too much on an unreliable input.
Right.
Which could lead to predictions that are off the mark. So sensitivity analysis can really help us spot those weak spots and guide us in refining the model or maybe collecting better data.
Yeah, that's really useful.
Yeah.
Okay, so sensitivity analysis helps us understand the relationship between inputs and outputs. But what about those weights and connections within the network? Can those tell us anything?
You're asking all the right questions. Yes, we can learn from those too.
Okay.
By examining the weights assigned to the connections between neurons, we can get a sense of how important different features and pathways are within that network.
So if we see a strong connection with a large weight, between a particular input and an output neuron, does that mean that input is really important for the model's decision?
Exactly.
Yeah.
And conversely, weaker connections, those with small weights, suggest those features might not matter as much for the predictions. It can be really helpful to visualize these connection weights to understand how everything's interacting within the network.
So we're creating a map of the neural pathways, sort of highlighting those most important connections and understanding the logic of the model.
Exactly. It's like lifting the hood and seeing how the engine works.
Yeah, I like that. This is really helpful for seeing how we can start to understand these black boxes.
It is, yeah. And when you combine that weight analysis with the sensitivity analysis, we can really develop a deep understanding of the model's behavior.
Right, okay.
But it's not just about applying these techniques on their own. It's super important to bring in our domain knowledge, too.
Right, we can't just trust the numbers blindly.
We can't, no.
We have to use what we know about mining processes and the context of the problem to interpret those results.
Exactly. Our expertise lets us see if those findings make sense and line up with what we know about the real world.
Yeah, for sure. Okay, so we've talked about sensitivity analysis and looking at those weights. What other techniques can we use to understand our ANN models better?
Well, there's a lot of interesting research going on right now in developing ANN structures that are more transparent and interpretable.
Okay.
One exciting area is the use of what are called attention mechanisms. They're kind of inspired by how we humans focus on specific things when we're making decisions.
Attention mechanisms, okay. How do those work?
Okay, so imagine you're looking at a complex mining scene, trying to figure out the risks of a hazard.
Okay.
Your brain automatically focuses on specific parts of that scene.
Right.
And filters out the irrelevant stuff.
Right, okay.
Attention mechanisms in ANNs are trying to do the same thing.
Okay.
They assign weights to different parts of that input data, highlighting what's most important for making that prediction.
So the model is showing its work, telling us what it's focusing on when making a decision.
Exactly. It's like having the model explain its reasoning, which gives us more confidence in the results.
Right, okay. This is really fascinating stuff. It feels like we're finally getting closer to understanding those black boxes, which is so important for us mining engineers.
I agree. And as research continues, we'll see even more creative ways to interpret and explain these models, making them even more powerful tools for mining engineers.
This deep dive has been amazing. We've gone from the basics of ANNs all the way to the complexities of interpreting those results. I feel like I've learned so much.
Me too. It's been a great journey exploring this together.
It has. And to all our listeners out there, I hope you feel inspired to dive deeper into the world of ANNs and see what you can achieve with these powerful tools.
Absolutely. The future of mining is intelligent, and ANNs are going to be a huge part of that.
And as always, NEXGROW is here to help you along the way.
We are.
We offer tons of resources and expertise to help you unlock those possibilities with ANNs in your mining operations. We do. So keep exploring, keep learning, and keep pushing those boundaries. And remember, the greatest resource in mining isn't hidden deep underground.
It is not.
It's the knowledge and the passion of mining engineers like you.
Absolutely.
So until next time, happy mining.